So hello everybody again. I'm very happy that Jozsef Lorinczi could, I hope I pronounced your name in the right way. Yes?
Yes.
Yeah, usually people make mistakes in my name, so so just I'm happy that Jozsef could join us today, and he will be talking about most likely location of paths for a class of Feller processes. Thank you, Jozsef. Please.
Thank you very much, and hello everybody. I'm really sorry not to be in the same room with everybody else, but I think that nobody is in the same room, more or less. The second thing is that, of course, or the first thing is that I'd like to start actually by thanking Jelena for this opportunity to give this talk. But even more importantly, of course, is for all what she has done for this whole series to take place, because I know it's not trivial.
Well, thank you.
Secondly, I have to apologize from the beginning in advance that I'm a complete beginner with this technology, and anything that happens beyond my will or wish may happen, and I just I'm at the mercy of this technology. But Jelena is a very good guide, and she will be helping me if anything goes wrong,
Don't worry.
Picture or sound or anything else. So yes, this is the story I'd like to discuss today or tell you today is about the most likely location of paths for a class of random processes, Feller processes. And I am going to take a bit longer than yesterday's extra lecture. So there will be a part 1 and there will be a part 2. In part 1, I'd like to discuss some a general introduction first. What are these processes? I'd like to say some things about what is a landscape, which I'd like to call a reward or penalty landscape or energy landscape, and how some random processes evolve in that type of environment. Why is this a good problem? That type of question. Then I'd like to introduce the main topic, which is the domain problem today. And then I'd like to say what actually the result is and just discuss it a bit. And then in the second part, I'd like to come to explaining how probability, geometry, and spectral theory combine, what are some interesting and sometimes unexpected consequences of this work, and how it connects to some other problems like the famous problem of hotspots, and another one, the torsion problem, because now I have 2 hours. So probably I also can speak about this other problem. I'd like to start with something that probably all of us know, the Steinholdenberg process. We know that from university or from everywhere else that if you start with an SDE like this, then you get to this process, which is called the Steinholdenberg process. This is the starting point, and this is an Ito integral. But the integrand is very simple, is not random, and we get this expression. And then it's immediate that this is a Gaussian random process, and it's also immediate to compute, therefore, its parameters, expectation and variance. And if you look at what happens when t goes to infinity, you will see that this process or the measure has a limit, unlike for Brownian motion. It does have a limit. It goes to a normal random variable, this one, for every t. So you are going to pick up this type of stationary behavior with this variance and that name. Also, we know how to compute its infinitesimal generator. So there will be the Laplacian, the one-dimensional Laplacian here, which is generating Brownian motion. And there will be a drift term, x times d over dx, generating the drift term here in the SDE. And one thing that also probably many people know, it's also standard, is that there is an intimate relationship between the drift, this bx term, and the stationary density, the measure that you compute by a limiting procedure here, so that the drift is actually the logarithmic derivative of the root of the stationary density of the process. Then, there is something that you realize, that there is another operator which is intimately related to this one, there is a unitary transform between this operator H, a number lambda naught, and the generator, or the minus generator of the Steinholdenberg process. And this computation is easy to do, and you will come to noticing that this H will produce a term on top of the Laplacian, negative Laplacian, which is this one here, this quadratic term. And this unitary transform, you mapping this weighted Hilbert space into flat Hilbert space, just by multiplication by this function psi naught, makes this interesting relationship between these two operators H and L. And then the relationship is that the stationary densities actually can be recovered as the square of this function. And this function is nothing else but the lowest lying eigenfunction, L2 eigenfunction of H. So psi naught is what we call the ground state, lambda naught is what we call the bottom of the spectrum of this operator H. Now, this operator does not look like this operator, but the two problems in a way combine into one. They are equivalent in some sense. So you can study some diffusion, this particular case, diffusions as equivalent cases in a particular sense, of course, with Brownian motion traveling in a potential landscape. So this means that you have some sort of extra term that is either rewarding or penalizing Brownian paths to go in particular directions, and these two problems correspond to each other. So then if you are wondering where should paths feel happiest, then of course it's going to be at the bottom of V, because that's the lowest energy cost, which happens to be also the peak, the location of the peak of the mode of the stationary distribution of M, and that's also a place where the drift is zero. So this is the most peaceful location for paths, and therefore this is some sort of an equilibrium. Now this is the Steinholdenberg process, but you can go on with this. So if you now change this x squared half term into something else, which I like to call a potential, then you get what is called a Schroedinger operator. So you have the Laplacian, and on top of it, you have this potential acting as a multiplication operator. So instead of x squared half, you have many other possible choices here. And then the probabilistic representation, the connection between this operator, which is now, the whole connection is now turned around, you see, because now I'm starting with this operator, and I'd like to get to L from H. This is then going to be possible via the famous Feynman-Katz formula. So that if you look at the evolution operator, evolution semigroup under H, then what you get is that you have to run a Brownian motion starting from X, and you average, you take the expectation over its paths, which are going to be weighted by these exponential densities, which directly depend on this V term here. So this makes the link between the operator language, if you want, or the PDE language, and the stochastics language. So assuming that this H operator has a ground state, a lowest lying eigenfunction, this is what it means, that this is the bottom of the spectrum, it's the lowest eigenfunction, then this is an eigenfunction because it satisfies the eigenvalue equation. We are in the domain, and this is, if there is such a solution, if there is such a phi naught, then actually one can prove that this is strictly positive, and we can normalize it, and then of course it's going to be a density, a probability density. So then the diffusion that we can derive from this new potential landscape is also explicitly possible to give, and then we get this drift term, which is now directly dependent on phi naught. And shall we again remember that this is going to, its square is going to be the density of the stationary measure plus the diffusion term. So the stationary density, like I said, is this one, and the infinitesimal generator can be again calculated explicitly, and you get this term for the diffusion again, and this term for the drift. This also allows you to change the measure. So if you now look at the process, this diffusion xt here, then its own path measure, which I call here P, is then going to be this expectation over this process xt, and that makes the direct relationship with no V involved anymore, because all the effect of V now is inside P, And then the effect of this is going to be this expectation directly in terms of data purely on the X process. This can also be made even more general, because so far what we did was to play with V. So we kept the Laplace, and then we put here another V. But now what I'm saying is that I even can give up the Laplace operator, and I can choose a function of the Laplace operator. And I'd like to explain why a bit later. In any case, I'd like to head towards non-local operators. So this is going somehow to be a non-local operator. And let's remember, what does it take to be a non-local operator? It means that the support of any function on which the operator acts is going to be bigger. So in a more profane way, of course, I could say that the evaluation under the operator at a point x of a function f is going to depend on other locations than just at x. Unlike for differential operators, because if you would like to take the differential, the derivative at a particular point, then you only need the data there. But if you have to make an integral, for example, then of course you have to integrate in a neighborhood or everywhere else. Who knows? Who are possible choices of this phi or minus delta that I may have in mind? There are many. Probably I don't have to explain these symbols anyway. Well, I will tell you a couple of things. This is what we call the fractional Laplace operator. I come back to this in a minute. This is what we call the fractional relativistic operator. Then you can take sums of them at two different exponents. Then you can take one of the exponents to be 2. Then you can take the so-called geometric fractional Laplacian, which is related, for example, to the gamma variance process. All these guys are related to processes. When alpha equal to 2, then this is generating the variance gamma process, which is known from financial mathematics. Or you could also choose the fractional Laplacian with an exponent that depends on the position where you are. So you change, in principle, you change the exponent at every step. Very interesting operator. And then the relationship, this Feynman-Katz formula, survives. It exactly reads the same way as before, with the huge difference that now it's not Brownian motion to play here anymore, but the process that is being generated, a jump Levy process that is being generated by this new operator, minus phi, minus delta. So then, who is the random process that you pick up? What is the SDE before? If I can go back quickly enough. The process that we had, the SDE that we had was just this, drift plus a diffusion term. Now it's going to be far more complicated. Now we're going to see here dVt, well now this is the integrated form. We're going to see the Brownian component, we're going to see this drift component, but we are going to see also a jump component. And here I'm separating the small from the big jumps. And everything is now determined by phi naught. So you're going to jump now in all sorts of directions, but not equally likely. It's going to be heavily determined by the values of phi naught, where you are, dependent on that, and also the directions. So V, what is the role of V? V is going to give a drift, which depends now on where you are, and it's also going to produce a bias in the jump rates, in the directions, and in the sizes of all these jumps. So to have an idea about what the V should be, it's not just the harmonic oscillator that we have seen in the case of Steinholdenberg, which of course is very simple and doable by hand, one of the rare examples. But this is a more real-life landscape, a more real-life type of V. And of course, this is what we would like to have in mind, that a process is traveling in between these mountains and valleys. And then, of course, it's heavily taxed according to it has to go uphill or downhill. And of course, therefore, all these probabilities are going to depend on the morphology of this V. Then, like I said, everything depends on phi naught. So it's crucial to know something about phi naught. Of course, I would like to have some explicit cases, and we know it in two cases. And I put here inverted commas because we actually know the Fourier transforms of phi nodes and every other phi. But I'm told people are telling me not to be too sad about this because that already passes for explicit. If you know the Fourier transform, that's already explicit. So I was glad to hear that and to learn that that's explicit. It's explicit because you really can extract a lot of information. And if you're lucky enough, of course, you can sometimes even back transform them. But in these two cases, you can't. I mean, this is going to produce an airy function. And this is also going to produce a heavily oscillating function. And it's not very trivial to transform them back. But of course, you can get a lot of information out of the Fourier transform. Very good. Now, how about these processes, which I wanted to call, again, I would like to go back very quickly if I can, but I am not so good at this. I would like to call this a GST, so-called ground state transform process. How do I get this? By this unitary transform, and then I get this SDE like I explained. And this is a name ground state transform process, which is, it depends on this ground state, which introduces all these position dependence on the diffusion and on the jump. I'd like now to connect quickly with yesterday's talk, with Nikolai's talk. He was explaining us something about the fractal properties of some processes, or well, he wanted actually some similar processes. Now, I don't expect that he is with us today because he's probably too busy. But anyway, what I'd like to say is that he was kind of getting very near to this yesterday. Just a couple of things about what these GST processes are like. You can measure its regularity, path regularity, locally if you compare it with a polynomial at that location. So if it is inside a particular error margin, which is expressed in terms of this exponent, which is the highest possible exponent for this approximating polynomial, then you call this the local exponent if you take the largest possible, the best possible exponent here. And then you can look at the so-called multifractal spectrum, which means that you are looking at all the points which have a particular Herder exponent h, and then you are keeping track of this for every h. So you look at this map. This is the so-called multifractal spectrum. Then what comes into the game is the so-called Blumenthal-Tour index, which is measuring the rates of growth around zero of the Levy measure. This is the Levy measure, which is a number between 0 and 2. And just to give you an idea for the stable process, it's index. It's just its alpha. And using this Blumenthal-Tour index, you can express something about the roughness or the niceness of parts of these GST processes. Something that we proved with a collaborator of mine, Xiaochuan Yang. If you take a GST process given by the complicated SDE that I showed you before, which is generated by a Levy process, so there was an underlying, instead of Brownian motion, you have a general Levy process with these triplets, so this drift, this diffusion, and this Levy intensity. Then these are the multifractal spectra. If you have a do have a Brownian component, then it's going to have a big impact. If not, then not. But first, if you do have a Brownian component, then when you have, what was h, if you remember? H was the exponent here, the Herder exponent. For Brownian motion, of course, we know that this is Herder continuous up to 1/2. So if you take 1/2 up to, well, 1/2 actually, then this is with the dimension 1, and this is the contribution of Brownian parts. For the jump, the contribution is given then in terms of this Tour index multiplied by the h value, and this is always less than 1 because beta is never more than 2, and h is just below 1/2 at best. So then this is how the jumping parts contribute. If you don't have Brownian component, then actually the story is more interesting, and I haven't seen anything like this in the literature before. If you can jump frequently but relatively little like this, or else if you jump big but relatively rarely, but the ground state or the stationary density, we should remember, is smooth enough, then we get this type of expression. Well, never mind, you can think about this later if you want, but just to compare this with a classic result, just for Brownian motion, we have one for every, almost surely, for parts when h is exactly 1/2 and we have nothing else. And then, of course, this is how it modifies if you have also the extra complications that I explained. So this much about the behavior of parts locally. The behavior of parts globally. What is the typical part behavior when we are looking at large times, long times? Then we would like to have a statement like this ideally. What is the time evolution envelope, if you want, on which, on the long run, the parts evolve? For Brownian motion, of course, we would know, and this y were just Brownian motion, of course, we would know that this is square root of 2t log lt. So this is the famous iterated logarithm. Question: what is the LEL? What is the iterated logarithm in our case for all these bunch of processes? And the answer is given by this integral test. You can construct this integral test, testing if a particular evolution envelope is possible or not against the stationary measure phi naught squared. And then what you can prove is that this integral test, finite or infinite, of this integral is going to decide if tau is or is not such an envelope. And then actually you can say that yn is something like a constant, which is important, of course, you would like to know that, times this deterministic function on the long run. This is then the expression of this, where this limits up. It means just that when time is large enough, then y behaves like this times this. So of course then you would like to know how this depends on, for example, if you just take a simple alpha stable process and you add this potential on it, then what's the effect? How do these envelopes change? That's your question. And from this general formula, you can then derive all sorts of specific behaviors by the taste or by your interest, which particular process you would like to look at. But one thing is very interesting to mention here. It's an old result by Hinchin. If you have just a stable process, no V here, no potentials, just a flat stable process, then there is no such thing as tau, because this ratio is either 0 or infinite. So there is nothing like a LEL behavior, nothing like a decent behavior on the long run. And all this picture changes dramatically. You're going to pick up a tau, a decent tau, if you add some potential. So a potential is somehow going to have some sort of a smoothing effect on a process which is as wild as a stable process, for example. So this is just to mention that you can play with this type of thing. And it's a very interesting question, of course, how these processes develop on the long run. Okay, I want to skip this one. I can come back to this. It just says that if a potential is growing faster than another potential, then the envelope is tighter than the other envelope. And you can prove, of course, this stands to reason, but proving it is it takes a little. Very good. Now I'd like to really come to, this is still my preamble of my talk, but I'd like now to come to a bit more regular discussion of what Feller processes are. All these processes I mentioned so far, they are interesting for all sorts of applications, and you see how they emerge. But they all fit into a bigger box of what we call Feller processes. So let me just quickly remind you of a couple of essentials about what Feller processes more generally are. So if you take a Markov process xt, and it has this transition semigroup, which is generated by just taking expectations, right? This is the standard transition semigroup. We say it's so-called strongly continuous if in norm, subnorm, it behaves like this for every function which is taken from this test space. So this means that you have continuous functions that go down to 0 at infinity. Then you say that you have the Feller property if this space is mapped into itself under this transition semigroup. And you have the so-called strong Feller property if bounded measurable functions turn into bounded continuous bounded functions under this property, under this semigroup. So this is of course extremely nice when you have strong Feller, because weakly regular functions get more regular, and here they are just inside the same set. So for example, of course, Brownian motion does have this property. Then, if these two properties hold, then we say that the process is a Feller process. And if all of them hold, then we say it's a strong Feller process. And again, something to just to know where we are on the map, it's good to know that Levy processes are Feller processes, and they are Markov processes. And of course, there are various steps in between. You can think about other Hump processes and other processes. And I'd like to mention a few names, of course, who have made many interesting contributions, let's say starting in 1980, what was that? 1998, it was when Niels Jakob was having a good idea how to introduce operators in describing Feller processes. And he kind of established a school, which was, well, without kind, I think. He established the school, and Walter Ho and René Schilling, well, I think that Franziska Kuhn, etc., etc. And of course, I would like to single out very independently Vasily Kolokotsov. Of course, he had some very interesting analysis, for example, of the stable process dependent on how's it called? Stable light process, which depends on which has indices dependent on the location, and they also go in this direction. Then, what do we know in general about these Feller processes? Now we know what our Feller process is. They also have a nice representation in a nutshell. In case the domain of the infinitesimal generator contains this important set, which is the set of smooth, compactly supported test functions. In case this happens, people even call this then a rich Feller process. I don't like this expression, but never mind. Then the operator L can be obtained again in a nice formula. This is not always true for a general Markov process, but for Feller processes you can do that. And there is this Fourier multiplier that is going to actually carry all the information about the operator and the process. And it can be expressed in these terms. Now, everybody probably would say that, well, of course I know this, first of all, because I know what Feller processes are, but secondly, because I know what Levy processes are. Because this is like the Levy-Shinchin formula, except that if you take a closer look, you see that everywhere, all the data depend on X. So this is a jump measure, which depends on where you are. This is a diffusion matrix, depends on where you are. This is a drift term, which depends where you are. This is a killing term, depends where you are. That makes the big difference that this is not homogeneous in space anymore. When there is no X dependence, you are back to Levy processes, and this representation survives when you add this X dependence. This is due then to Courage and von Waldenfels. Another important thing about Feller processes is that they are semi-martingales, and these are the characteristics very quickly, never mind. If you know the story, then you know what I mean. But it's important to know where they are, of course, in general. So all these SDs can be written down about these Feller processes. One thing I'd like to single out is that there is a lot of activity about general Feller processes these days, but most of the literature, I know at least, is about cases of bounded coefficients, which means that the Fourier multiplier is uniformly bounded in X on the location. And of course, there is this obvious bound in Y, but it's uniform in X. And all the GST processes, ground state processes I mentioned to you, they are not. That just means that I cannot apply the standard mathematics to understand my processes. I have to do something extra. But all this nonlinearity and unbounded coefficients, they really introduce a lot of of course, difficulty, but also a lot of joy into this, because you see something, some of the things happening. Okay, then what do I want to talk about today? So now what I want to do, all these ingredients, now I would like to put everything in a domain. This domain is going to be bounded and it's going to be convex for technical reasons. And then I would like to run the process and look at this operator, confined. Well, that's not the word to use probably. Nobody wants confinement anymore. But this is something that I just want to look at in a domain. So the analytic problem is this type of eigenvalue problem with an exterior condition. So it's not a boundary condition that you have because of the jumps, but you have to condition everywhere outside the domain. So this is the complement of D. There are all sorts of good reasons why this problem in itself is interesting, but you can read it, but let me not discuss it. But my main focus today would be, where is the or a global maximizer or a global minimizer, which I want to call X star, of the solution of this eigenvalue problem of phi. And again, remember that phi naught, the lowest lying eigenfunction, is actually the square root of the stationary distribution of the process, which we already discussed. And its maximizer, therefore, would correspond to the mode of the stationary distribution. So this is, in this sense, the most likely location of parts. So therefore, this is what we want to pursue in this talk. So what I'd like to do then is to explain a bit all these who's who, all these ingredients, then to tell you what the result is, and then the consequences, connections, like I promised from the beginning. Let me go back to subordinators. Again, this is something that people might be very familiar with, but very quickly. A subordinator is a Levy process, which is almost surely moving upwards, never downwards, non-decreasing. So this is expressed very clearly by this line. And it has, of course, various nice implications. First of all, of course, due to stationarity, that means that this is positive value of this process. The Levy-Shinshin formula is going to simplify to this. Automatically, the Brownian component is out, because, of course, that would not be compatible with moving only upwards. And everything that can survive is the jump measure and the drift. But the drift has to be positive, because you are going to have positive values. And the measure also cannot live on negatives. It only can live on positives. Therefore, I'm integrating from 0 to infinity here. And something that you cannot immediately guess from this formula is that the Levy measure of a subordinator integrates better than a general Levy measure. It integrates against y instead of y squared. And the reason is that the cutoff term, which, if you remember, also would contain a y times, etc., that is missing. And therefore, this will be just coming to y. Another general fact about subordinators is that the Levy exponent, which is of course defined by this formula, as you would know, is a Bernstein function, and it's a so-called completely monotone function, which means that its derivatives flip sign from one to the next. So that they are positive, they are increasing functions, they are concave functions, and so on and so forth. Why actually I can take in the Levy-Shinshin formula just the Laplace transform? The answer is immediate, just because everybody is positive here. So I don't have to worry about characteristic functions, complex functions here. Everything is just Laplace transform. And it's something very plain and very nice to know about the Laplace exponent. It looks like this, always depends on two parameters, this number and this measure. And they actually have this property, if you want. And then there is a bijection between the set of Bernstein functions and subordinators with these parameters. So you can always get from one to the other one in a unique way. Then you can use now these subordinators as new times, because they are positive, you can use them as new times, and you can look at Brownian motion at this new random time. This is called subordinate Brownian motion because you're subordinating it by his subordinator. This is a Levy process with all these parameters, so I don't want to recite this, you can see this, but what I would like you to understand is that everything is known about this. Everything is as explicit as more or less as it gets. It's very nice. And the generator of subordinate Brownian motion is just this Bernstein function of the Laplacian because of the relationship I just told you before that, you will see perhaps in a minute. So that in the end, what we have is that the transition semigroup can be then expressed in terms of this expectation. So we have to then take average with respect to Brownian motion and with respect to the independent subordinator. So now we are sampling Brownian motion at random times, which are given by the paths of this subordinator. And then this gives us this new random process, and it will be jumping. Just because I think that we have possibly some, do we have students or postdocs? I don't know, but
yes, maybe. We have PhD students.
We have PhD students, very good to know. Okay, perfect. So just because I think this is so important to understand how actually subordinate Brownian motion comes into this game. Why is it not just something else? This would be the slides. Maybe you can read it later if you want, but I can very quickly go through it. So if you're looking at what is the effect of this operator, so you're looking at the transition semigroup, but now I'm taking the scalar product in R2 sense with another function. So E2 minus T, this operator 5 minus delta, then just by using general functional analysis spectral representation of this operator, then you can write it in terms of the spectral measure of this operator. But if we remember who was this E2 minus T phi, we should remember that it was this one here it was the Laplace exponent, the Levy exponent, if you want, of the subordinator. So we have this relationship. I can replace this by that. Then I can apply Fubinian swap integrals, and then I can make the inside integral first by using again now the spectral representation of whoever is here. But now I don't have phi of lambda. I only have lambda, which is the same as here. So this is the spectral measure again, and then this combines into just simply the Laplace operator. So now what I get is that the Laplace operator is multiplied not by t, but a random time, which is st. And then of course I can use again the formula for minus delta for the transition operator, and then I can rewrite it this way. So I get in the end this one here. This is how subordinate Brownian motion is smuggled into this. Via the subordinator, just because of this procedure, how you can combine them. So this is going then to be our main class of processes, and you can appreciate that there are many such processes which are covered by subordinate Brownian motion. For example, the stable process, the alpha stable process, is such a subordinate Brownian motion. We just had this Levy-Shinchin just on the slide before. And if you make a calculation using just plain analysis, you will see that this is a tautology. You can make this integral at the right-hand side, and you land at the left-hand side just by this simple expression. And then it's by simple comparison. It's, I don't know, pret-à-porter if you want. B is out, 0, and then everything multiplying these brackets is mu. So then, of course, this is mu, and B is 0. And then these are the parameters of the stable process. So now you know the stable process, which is generated by an alpha half stable subordinator. And its generator is then going to be the square, we said, of phi at square of the variable. So if you plug in phi, then of course this is what you get. And then, of course, we have this expression for the transition semigroup once again, now for the fractional Laplacian. So here, now we are running a stable process, and then we have this relationship. Just people who are interested in analysis, or well, this is still probability, is that actually this expression, either of them, is just the fundamental solution of this equation. Many such equations probably you have seen in the course of these lectures. Here, what is a fractional is in space. It's the fractional Laplacian, but it's ordinary time derivative. It's no capital derivative or nothing like that. Then, yeah, so what is the fractional Laplacian? Just in case you don't remember, the fractional Laplacian actually looks like this. It can be expressed in many, many alternative ways. One is in terms of this singular integral, and another one is this more regularized, very handy expression, etc., etc. There are many more, but this is a non-local operator because to get the answer at x under this operator of a function f, you have to look elsewhere and you have to make an integral over the other variables, and that makes it non-local, unlike differential operators which only depend on data in x. So instead of telling you a whole story about stable processes, let me just show you what they look like. If alpha is small, then you typically jump big, but you typically jump rarely. And as you start to increase alpha, then these jumps are going to be smaller and smaller, but they get more frequent. So then at 1.5, this is how it looks, what it looks like, 1 and 1.8. If you have a good screen, better than mine, then you see a good resolution that they are still jumping. But if you take alpha equal to 2, all these dots would join into a continuous curve, and then you pick a branch motion. Good. So who is then the potential, this other ingredient? Now this is getting then technical, and I'd like to skip it. But it's important because otherwise, of course, it's a little bit moving in a bit of vacuum, unexplained. But let me just say that this can be very well controlled, and this potential landscape, if you want, can really be very rough. It can be very rugged, if you want. You can have all sorts of local singularities. You can take a look at your pace if you are interested later. But one thing why we are taking the so-called Kato class of potentials is that they are a very natural class for the Feynman-Katz representation to hold. And this is due to Chasminsky's lemma, which can be extended also to these processes, which means that if this expression is integrable for integrable, then it's also exponentially integrable, and that's what you need in Feynman-Katz representation. Then, who is my Schrödinger operator and the domain Schrödinger operator? Because now we would like to discuss everything in a domain. So then, shall we put the ingredients together? Yeah. Then we take a Bernstein function, but I would like to restrict to be equal to 0. So just jump, purely jump process and no drift. That also means that there is no Laplace operator in the expression of phi minus delta. Then we can define on L2RD full space this sum. Of course, this would need some discussion because this is both are unbounded operators, etc., etc. So what is the meaning of this sum? But it's a form sum. You can discuss this. Let me skip it. Then you take your bounded domain, whichever you wish. And then, of course, the question is, how do you define the domain Schrödinger operator? And then the answer is that you restrict first this operator on big space. You restrict it to this one, compactly supported smooth functions in D, and then you make the unique canonical extension by closing this operator, etc., etc. There is again a procedure, but this is fairly standard. If you know this operator theory a bit, then you will know what this means. But what I'm trying to say is that from now on, I'd like to use this domain operator. One thing that I'd like to say again is that it's no good, like a lot of the literature suggests, that if you can do something for the fractional Laplacian, then you have understood everything. It's not true. The fractional Laplacian is a very interesting example, and the usual Laplace operator is somehow its whole opposite. But there are plenty of other operators in between. For example, this exponential operator. It's neither like this nor like that. It has its own life. And actually everything comes down to what is the tail behavior of the jump kernel. And if you are sub-exponential, including polynomial, then you are well represented by a fractional Laplace operator. But if you are exponential, when gamma is 1, and then you could have all sorts of nuisances here, like a subleading term. This delta could be positive or negative, but what is essential if you are is that you have an exponential here, not sub-exponential anymore. Then you are well represented by this operator, and I really can tell you that these two operators massively differ. This really produces a very different, on occasion, and dependent on the context, not on everything, but it really produces a lot of different behavior than either of these two operators. It's a good mediator between these two operators. So there is plenty of reason, at least to me, to really look at the whole bunch of operators and not make my focus on this operator alone. Good. Then we need the Feynman-Katz semigroup, and this is something that I massively want to jump over. Of course, this is terribly important because you need to see how all these things are defined, but they are well defined. So at this stage, I would like you to believe me that all these objects make sense. Of course, there is plenty of difficulty when you have a domain because you have to close this operator, and the boundary of the D could be terrible. And then all sorts of properties would not be preserved if the boundary is terrible, or if this D is terrible in some sense. But what I'm trying to say is that for a good selection of the actually just convex bounded domains, you can do all these nice things, and you pick up all the regularities and regular behaviors that you would like normally to have. So let's skip this one. Then, what is the problem that I'd like to look at? I wanted to look at this equation under this external or exterior value condition. So conditioning to putting 0 everywhere outside of D, which now I claim, without having proven it, but I argued a little bit, that this is completely equivalent to look at the problem in terms of the domain operator, this one here. So I don't have to do this anymore. I'm looking at this one directly, which embodies, which also includes the exterior value condition. If you exponentiate it, then you can express this, re-express it again equivalently in terms of the evolution semigroup, this one here, which now, of course, is the one for the domain D that you have selected. And just to know that we are not talking here empty space again, there do exist such lambdas that solve this equation, whether you have a V or not. And then these would be what we could call Schrödinger Dirichlet eigenvalues, and these are just plain Dirichlet eigenvalues when V is equal to 0. And then the solutions have this probabilistic representation that you have again e to minus integral of V, now also be minus lambda because of this one here, phi, and the boundary condition or the exterior condition comes in by this restriction here. This is, did I forget to say? Oh, I did. I massively did. Tau D is the first exit time from D of the process X. So it's the first time that you are out of D, it's a random time. And you have to condition on it like this. Okay, I am nearing the end of my first chapter. This is going to be a bit longer than the second one. So let me try to finish this one first. Then it's more natural to break, and then we are going to have our break. So again, this was our representation of the solution of this boundary value, well, exterior value problem for given domain D and for all these operators. Then, what did I want to do? I wanted to do the location of the global maximum. So put here x equal to x star, where phi is maximized. For simplicity, let me just choose bounded V, but I really can do it for rough V. Now look at what happens. X star goes into here, so it's up here, right? No x dependency inside. But then you can take out this one just by maximizing it. Then you can take out the e to lambda t part, which was already out. And then you can somehow estimate away V by taking its negative part separately from the positive part. And then everything out, then it's the expectation of this, which means that this is the survival probability of the process starting from x star. And the nice thing is that I don't have to know anything about this. It cancels. And then everything boils down to this sort of inequality, this sort of inequality. But there is the nuisance, the inconvenience, that I'd like to know something about this guy here, x star, but it's not really the best position it may have. It's up in px star. And from here, of course, I would like somehow to learn what is x star. How can I estimate x star from this expression? It looks like mission impossible, because p is a probability between 0 and 1. And the whole thing has to be larger or equal than 1. So, of course, this gives me some idea how to try to excavate something about x star. Now, let me tell you two statements. One is the more general one, which I'm just stating. And the second one is a bit more friendly, and it's easier to understand. To get the most we can say about this, we need some sort of condition, some sort of scaling condition on phi. And this is what we call, it's actually, this is not my invention. This has been introduced into literature before. It's called weak lower scaling condition. So you see it's kind of self-explanatory. So it's some sort of homogeneity of phi, but from below only, and with an exponent. So scaling is a good word. Then, if you have this scaling property with these parameters, V is from this nice class, but V minus, the negative part, can be very rough. Well, not very rough, well, not arbitrarily rough, because V has to be like this, at least. Then we get this sort of estimate from this formula here. We get this sort of estimate in terms of the distance of x star from the boundary of the domain. This doesn't look very explicit because it's under phi, but it combines with the parameters of the potential landscape, so V minus, V plus, something about it, and lambda, and some constants. This is the best thing, or somehow the strongest thing that we can prove. But if we make it more gentle, and we give up rough Kato class type potentials, and we make them bounded, I make them bounded now, then everything gets more, well, a bit more friendly and more doable. And there will be a bonus, because those big thetas, theta 1, theta 2, they disappear. They are very much parameter dependent. But now we get a universal behavior. We get a number, small theta, which is about 1/12, which is going to enter this expression and nothing else. And it's, like I'm saying, an absolute constant. So if phi is strictly increasing, which is many, many cases, then we can explicitate how far you have to be, or how far is this most convenient location for parts, x star, which is the maximizer, we remember, which is the maximizer of phi naught. Well, if I choose phi naught, is the maximizer of any of the eigenfunctions. But in particular, if you take the lowest eigenfunction, then this is the answer. How far I have to, how far the most convenient location of parts is from the boundary. And the answer is that this is determined by this lower bound. And the lower bound depends on the non-local kinetic term, this phi, how you choose it. And this is how it depends on the potential. Somehow the strength of the potential comes in. This potential could be arbitrarily bad. Of course, now I have chosen it nice, but what I'm saying, it could be, for example, could be continuous, or it could not be continuous. It could be smooth. It could be anything. It is bounded. So therefore, this infimum and this norm, they are kind of measuring also the strengths of the negative and the positive part. And then this very nice number theta. So this is the answer, and this is somehow the solution of the problem. Why is this interesting? Because you remember what was the original problem? We had a Dirichlet problem. So that means that the process starting from this x star moves all about. When it hits the boundary, it gets killed, because then the eigenfunction is equal to 0. So it's simply getting killed. So therefore, this is somehow telling you what is your safe distance from the boundary, where you can accumulate, where you can cluster. So the highest clustering is at least this much away from the boundary, where it feels also safe, because it is not getting killed very quickly. Okay. Now, if I want to get back, just choosing phi equal to identity, which is a possible choice, it's a possible Bernstein function, then I can recover a result which is also very recent by Rach and Steinholdenberg, and they have proven it under some different assumptions, a very similar type of formula by using just bounded B. But we have done it here for many more domains and arbitrary dimension and very different processes, they very different potential landscapes, etc. Okay. Now this is something I think in the circumstances I'm going to skip, but I understand that these talks are going to be made available to the attendees, so you can take a look if you want. And the rest is consequences. So let me draw a close to the first part here, and let's have our break, and then we can continue after the break. But of course, if there are a couple of rapid questions, of course, it's up to Jelena to organize everything, so I really don't want to change anything about the format, but I'm happy to take any quick questions now before the break, if there is any.
Okay, well, thank you very much. It's very interesting and very understandable. Thank you again. Any questions so far on the material that was covered?
By the way, I think it's very easy for me to blush when a question is going up, because it's super difficult to ask questions. I think, first of all, of course, there's a lot of material. Secondly, we don't see each other, etc. So this is, you better watch the birds outside or anyway listen to them. So don't worry if there are no questions. Then we should have a cup of coffee in the meantime.
Yeah, well, just a very, I just came into my mind if I would like to ask that. So, you know, this constant theta you introduced, is there any physical meaning?
Unfortunately, I am not able to relate this easily to a physical meaning, but maybe I'm going to give some indications about in the consequences bit about it. But this is something like this, and it's not immediate to this. F is the distribution function of a Gaussian with mean 0 and variance 2. So this is a number. And then here you see a kappa, there you see a kappa, and then you have to take the minimizer of this function. I think it's a bit technical, to be honest. It does not have an immediate meaning, but it plays well. You will see in the consequences. And now as we go into applications, probits is going to be a bit more interesting.
Okay. So if there are, thank you very much. Yeah, again, if there are no questions, we just have a break for 5 minutes, and 2:05 we return back.
Excellent. I'll be there. Thank you.
Thank you. Hi, Joseph, are you here?
Yeah, yeah.
Yeah, hello. We have actually a question from Ned Watkins.
Okay.
Yeah, so are there any path integrals for the fractional time case? Or is this impossible because that is not Markovian? And then he writes more, by fractional time, I mean a diffusion equation with a fractional time derivative rather than a fractional space derivative.
Yeah, I think there are, but I am not the best person to ask this. This is more like Enrico and Vasily and of course Julia Mishura. But as far as I know, yes, you can have all sorts of Feynman cuts type formulas again, but it's different because it's not going to be a semigroup like the question implies. But I think that there are some. I mean, you take inverse subordinators and you have all sorts of expressions. But I thought that Vasily was explaining this type of probabilistic, probabilistic interpretations or probabilistic representations, and they are the path integrals.
Thank you very much. You can, I just remind you that you can always unmute yourself and ask the question yourself. Yeah. So that's perfectly fine.
Okay. You mean myself? No.
No.
I'm not asking myself a question. Yes. No, okay, I understand. Okay.
I'm talking to Nick. I hope you heard the answer. Yeah, I just Oh, hello. Yes, Nick.
That's fine. Thank you.
Yeah.
I can't see myself at the moment, but yes, thank you very much.
Yeah.
That's fine. I'm interested in this stuff because I've worked quite a bit in statistical physics, where there's this kind of semi-orthogonal conversation about things like the fractional Langevin equation and whether there's a difference between, you know, what the differences are between various types of fractional process with a physical motivation, if you like. So there's the continuous time random walk with heavy tails on the waiting times, and there's other types of Langevin equation which don't just have the fractional Gaussian driver, but they also have a more complicated damping term. They have a fractional operator as a damping term. Okay, so we can come back to this another time, but
yeah, I understand your question, of course.
Yeah, no, I'm sure you do.
The Langevin equation would be something like this. I started with this one here.
Yeah.
Here you could, of course, put another process, like a Levy process, DLT.
Yeah.
And that would be a Levy process driven on Steinholdenberg process. Many people are looking at this.
Yeah.
It is not time fractional in any way.
No.
But you can have it in this sense fractional. And
Yeah.
I think that there are also some others, because some people would indeed put here all these time change processes. So it's not the driver which is necessarily fractional, but the whole thing can be fractional. But this is, I thought, once again, that this is the other people speaking of. They've been speaking about all these time fractional business. I am the odd one out who is not.
Yeah,
I am not talking about fractional times.
That's fair enough. No, that's quite understood. I
still can answer one question to you if you wish.
Yeah.
If you change the time, you slow down the process. So just because you don't have exponential waiting times anymore, you know, on the microscopic scale, if you wish, then the process is not going to be Markov anymore, because it's not exponential waiting times. Right. Then you lose Markovianness. That means that you're going to have some sort of a length of memory back in time. Yeah. But you get all sorts of processes that have a different speed how they evolve. This could be this what is slower than diffusion, or it could typically, this is the case in here. But there are also models where you speed up diffusion. Yeah. But really, this is the cup of tea of other people.
No, fair enough. Can I just very, very briefly just explain that what I was actually talking about also was, you know, you've got that minus alpha xt term there, the standard one. Yeah, there's quite a lot of interest in physics in problems where that whole term is replaced by a fractional operator. So it's essentially, it becomes something like a Riemann-Liouville integral acting on X.
Okay.
And that's like a small industry called the fractional Langevin equation.
Okay, I see what you mean.
Whether or not there's been any maths interest in that is hard for me to determine. But it's not the same as the fractional Steinholdenberg process, but it's physically motivated because the kernel has to relate to the noise in these problems. Right. So if you make the noise fractional, you have to make the kernel fractional as well. Sorry, you have to make the damping term fractional as well. So I mean, it's a question for another day and another speaker, but I'm mentioning
probably another speaker.
Physical relevance. Okay.
But anyway, I appreciate the question.
Thank you.
I'm just not the best place to answer
understood. It. Yeah. Thank you.
Okay, thank you very much, and we will continue with the lecture.
Okay, so continue with the lecture if you're still interested. What are then the consequences? I'd like to explain some of them. So what did we do? This is going to be the main formula. I really would like to take now the easier case of just bounded potentials. So this tells us how far the location, the favored location, should be from the boundary, and this is expressed like this in terms of the data of the process, this phi, and in terms of the potential landscape. So now I'd like to explore what are the implications of this frame formula. One thing is that this location x star is related with a balance of the survival times, of particular survival times. So first you can try to interpret this expression, this functional. This actually means that you have this, if you forget V, then this is just the survival time of the process inside D. But if you weigh it by V, then this is the mean survival time in D under this potential landscape. And then this is being bounded by the corresponding eigenfunction from below, this reciprocal. Another thing is, that is generally known from potential theory, is that if you take the symbol of the operator phi, or the Levy exponent, they are the same thing, and if you take it 1 over r squared, then this is proportional with the mean survival time of the process, of the free process, no V process, in a ball of radius the same r. So therefore, if you combine these two things, and if you go back to the framed formula, then you can make all sorts of choices. But if you make this easy choice that you only have V minus part and no V plus part, then the condition that I have in the framed formula can be rephrased like the mean survival under V has to compare well with the mean survival with no V in the same domain. And that's an equivalent phrasing of how far you should be from the boundary. Another one is that indeed this is also doing something about safe distances. If you have a potential, you can imagine, that has a hole, a negative part, deep enough and close enough to the boundary, that means that this is very attractive for parts to spend their time. And it's also very dangerous, because if you start from there, you have a higher chance to hit the wall very quickly, the boundary very quickly, and that means that the process is killed. So therefore, it's not very safe. And still, we have that relationship. So the question is how close you can get to the boundary. So if you look again, what was the formula? The formula was that the distance is at least this expression. So now I'm turning it around, and I want to call the lower bound this expression. And what turns out to be the case is that I can compare processes which have heavy tail, exponentially light tail, or they are diffusions. And they are in this order somehow, in terms of the ground state energy. This one is producing the smallest ground state energy, this one the next, and this one the third one. And that means that if you have a process, then this lower bound is the smallest for Brownian motion. Sorry, not for Brownian motion. For a jump process, for a alpha stable process, and it's biggest for Brownian motion. So if you are playing this game with Brownian motion, then you can be quite near the boundary, because Brownian motion is going to hesitate a lot. It is evolving, it is fluctuating continuously. So there is no immediate danger that is just by one move is going to hit the boundary. But if you are a stable process, then this has to be a smaller value, a bigger value, because there you have the danger that by a single jump, you hit the boundary. So this makes also a difference, and an ordering in some sense of the processes dependent on how dangerously they evolve from this point of view, that you can hit the boundary by just one single move, or your jumps are typically exponentially suppressed, or if you are Brownian motion, where you are just moving back and forth all the time, and you are not immediately running the danger of hitting the boundary. So this is what it is expressing, this one here. Oh yes, and I would like to, if we have also some physicists or physics inclining people, then of course I would like to call this an entropic repulsion type of phenomenon. That the boundary is actually repelling. It's like an effective force on the process, saying that don't come too close to me because you die. So it is kind of exerting some sort of a force which is against the natural wish of processes to fluctuate freely. And the compromise between this entropic repulsion, they would like to increase their entropy to fluctuate as much as they can. But if they are too close to the boundary, then they cannot fluctuate enough. So therefore, this entropic repulsion. And then the compromise, somehow the equilibrium between free motion and this entropic repulsion is going to fix where x star should be, where you should accumulate most in front of the boundary. Okay, then there are all sorts of other consequences in terms of energies of the spectrum. For example, there is one purely probabilistic expression that all the energy values, if you want, or all the eigenvalues are reciprocals of these mean survival times, starting from the most favored point, from the x star. Then there is a purely geometric one. You can put here somehow the biggest value of r. You can estimate everything away by the in radius of the. This is the radius of the biggest ball that you can draw inside D. That's the in radius, and that is uniquely defined for a D, for a domain. So that gives you a a kind of a uniform bound on the spectrum, which is also nice for people interested in this thing. And Jelena was asking what is theta, if we can give some sort of a natural understanding what is theta. So for example, from here you could say that theta is somehow the best constant that is going to maximize this divided by this, the ratio between the this again is some sort of an energy functional, if you want, and this is the biggest thing that you can have in the domain is inward. So you can try to to speculate from here. Then, if you don't have a v, you don't have a potential function. Then you only have the Dirichlet eigenvalues, and here you get all sorts of expressions that were not existent in the literature. People know that for stable processes in a domain, not even for every alpha, just Cauchy processes, but they don't know it for other processes. But here you can have all sorts of bounds on the Dirichlet eigenvalues purely in terms of the survival time. So this is the expected, is the peace moment, if you want, of the survival time inside the domain, and so on and so forth. Expressions like this. So this is useful because these are consequences on the Dirichlet eigenvalues, which you may or may not have expected to see from that very innocent-looking estimate. Then I'd like to speak a bit about an isoperimetric behavior. This is the famous so-called Faber-Crown inequality. There are many, many isoperimetric inequalities. People are interested in all sorts of optimization problems. So if you go for instance, to convex geometry, then we know, if you just go back to planar geometry, that among all the shapes possible of a given fixed perimeter, the largest area is enclosed by a disk, right? So you maximize the area inside by fixing the perimeter if you turn it round. And you know where is Nördlingen probably. And there are many other cities which have been built on the same principle. In spectral theory, there is a similar type of interest. So if we have an operator, then of course it's a calculation, and we may or may not be lucky with the calculation to determine the eigenvalues. So we have to solve an eigenvalue equation, and then we get the spectrum. But people are asking also the opposite question. If I know the eigenvalues, can I determine what is the domain generating it if I know the operator? So this is an inverse question in spectral theory. Mark Katz was, in a more poetic way, he was asking, can we hear the shape of a drum? And the drum would be, of course, the domain, and it's about hearing them because all these eigenvalues are actually vibration frequencies of a membrane. So that's the drum. So the general answer is not. We cannot reconstruct just by knowing what the eigenvalues are. But people had to work on this. And the first counterexample has been produced by the famous geometer Milner, but in 16 dimensions. So people were not sleeping well for a while because it's probably not the most natural answer. And you had to wait nearly, 30 years to get down to 2 dimensions. And these 3 people constructed 2 so-called isospectral domains. That they had the same set of eigenvalues, but these 2 domains were not congruent. And therefore, unfortunately, in principle, it is not possible to reconstruct the domain by knowing how it sounds. But not everything is lost, because we somehow can hear round drums. So if you look at the bass tone, the lowest eigenvalue is minimized by a ball. So if you take all the possible Ds, which have the same Lebesgue measure as, for example, a unit ball, and you compute for each D the first eigenvalue under Dirichlet condition, then the first eigenvalue, lowest eigenvalue, is going to be the smallest if and only if D is a ball. and there is a single minimizer to this problem, and that's just the ball. So we can here, if we heard everything, then at least we have been able to distinguish the perfectly round-shaped drum, but only that. Now this is the so-called Faber-Crown inequality, this one here, one version of it, and people have been working a lot in this, in geometry and in spectral theory and in analysis and in all sorts of applications. One extension direction is what happens with these minimizations, maximizations, if we now take another operator. So some people have been looking at trying to take fractional Laplacian, but only with alpha equal to 1 and no v. And they also came to a conclusion. Another way to do that is that we add a v, and we still have classical Schrödinger operator. And this was a famous paper, which has appeared in the Annals of Mathematics this year. So you see, it's a recent result for such a basic question. And then this is the expression of the Faber-Crown inequality when you have a v function as well. This omega d is the volume of the unit ball in d dimensions, and j is the first zero of a particular Bessel function. So again, this is a minimization by balls. Now, what we get from, once again, from just this, that we know a lower bound on how far we should be best from the boundary. Looks very innocent, but it implies the Faber-Crown inequality. This was a big surprise to me. And what we get is this is our result, which is very similar to the Cardian Hudson, except that of course now we have phi minus 1 because we do it for the whole bunch of operators or for the whole bunch of processes, if you want. This theta, when in their case phi is just and phi minus 1 is just identity. So forget this, and then you get back here. And then you take this theta and you multiply. Instead of JD, you will have theta to d half, this side. So it is the same. It gets back to this inequality. But our constant is not really good. For example, if you take 2 dimensions, then this is the sharp constant. Ours is 70 some times away. So it's really a bad constant. But I'm still very happy that in essence, we get back the same type of behavior, and we get back this famous inequality just from our estimate, even if the constant is not so good. Other things you can also find, if you're a probabilist, then you're interested about existence of exit times from general domains for general processes. And what I'm saying here is that you can have again some geometric bounds, both up and down, below and above, on the mean survival time, mean exit time, and even their moments and exponential moments. These things were simply not known before, not even for stable processes, some of these things, and they really follow so simply from that estimate on x star. Now, I'd like to close by two problems that somehow relate. And one is the famous problem of hotspots. So now we turn the page, and I did. So what we have here is it's a different problem. Here you have a parabolic problem. So here you have a time evolution, and this is the usual Laplace operator. So you want to solve the heat equation in a domain like this. And you put this boundary condition, and you put this condition inside. So what you are doing here is that you are, I don't know, just heating up a plate, and you are asking, if you wait long enough, where is it going to be the hottest? So what you're looking at is the maximizer of the solution of the temperature, if you want, the solution the location of all points that at any given time point make the temperature the highest, maximize the temperature when you close the domain. So then this is the set of all the maximizers of the solution of the Heat's equation at a fixed time. Then you can prove that this set of points, the set of maximizers, is actually a subset of points for which the solution has an extreme in the sense of usual sense. And as time is getting long enough, larger and larger, then this is going to be a singleton, a one-element set, x hat. The solution of this one is going to be, the maximizer of this one is going to be x hat. And what you can prove is that when t is really going to infinity, then the set of the maximizer of u, the hot spot, is going to converge to the maximizer of the first Dirichlet eigenfunction indeed. Exactly what we are talking about. And this is a famous problem, and many, many people have been considering it from the earliest of times, if you want. So somehow the hotspots would converge to the point that I was interested in. There is, if you know this, you might want to connect and remember that there is a famous version of the problem for Neumann boundary conditions. This was Dirichlet. But there is one for Neumann boundary conditions. There is a famous conjecture by Rauch, which for a long, long time people have been trying to prove, and it turned out to be false. These people, Burzi, for example, very much, Wendelin Werner, they've been constructing some domains for which it was not true. But then if you restrict the class of possible domains, not an arbitrarily convex D, then actually it becomes true. But this is not true without any proviso anymore. And here actually the Rauch conjecture would say that the hotspots are not converging to the maximizers of the first Dirichlet eigenfunction, but they are converging to the boundary. So hottest is at the boundary if you have Neumann boundary conditions. If you have Dirichlet boundary conditions, then the story is very different, because then it is pulling over the maximizer of the Dirichlet eigenfunction. But I have nothing to say about the Neumann boundary conditions. I just wanted to mention this just because you might know this one better than this one here. This one is more famous just because of the negative news that they have been false. But this is an equally interesting problem, and I have something about that one to say. What we get is that the location of the hotspot, x star, can be estimated like this, purely in terms of the in radius and a number. And people are still interested very much. I've seen a very recent paper which appeared in June this year, just last week, by at least one of these people. I think it was Lorinczi. But these people, I mean, some 10 years ago now, more or less, they came to this type of best lower bound for how far is the hotspot from the boundary. And again, our calculation is really a big improvement over this one. So this is the in radius, this is the diameter. So of course, if you increase this d to make it large, then of course this is getting worse and worse and worse. And we only have the in radius. Okay, so this is what I wanted to say, I think, about the hotspots. Then I would like to really finish by just a comment on the torsion problem. What is this? This is a completely different story. This is another equation. So take again a bounded domain and look at this equation, minus delta equals 1, and you have Dirichlet boundary conditions. And compare it with the eigen value equation under the same circumstances. And then people have noticed, especially later in time, that the maximizers of the solutions of these two very vastly different problems, here you see it's 1, and here is the function itself, they make a near miss. They are very near to one another, the location of the maximizer, but they miss each other. They are not the same. So for example, if you choose D to be these right isosceles triangles, these two, then if you look at where is the hottest, and again, well, not the hottest now, but where do you see it most red and where do you see it most red here? Then these are the coordinates. The maximizer of the torsion is 0, and this coordinate, the other one, is different, you see, starting from the 4th digit, which is crazy in a way. It's not easy to imagine why on earth they should take their maxima, these two entirely different problems, more or less at the same place. If you take the half disk, which is not pictured here, then you get again some similar sort of behavior. So it's 48022 versus 48051. So this looks like a very interesting problem. And this is again an old problem. You can see that actually Mackay, 1962, a countryman of mine, started this problem looking at the torsion, because this is interesting in statics, in mechanics, that you are looking at this so-called torsional rigidity, which is this type of functional which you would like to maximize. There's a story behind this. So again, just mentioning this if you know what it was. And then there are some famous inequalities by Saint-Venant and Kohler and Jourdain. And if you put these two things together, by the way, you get back to Faber-Crown. So this is an interesting functional, this torsional rigidity. And what we are talking about is its maximizer, this here. And in our paper, of course, we could look at the non-local version of the torsion equation, which of course could be also the local one, because phi could be the identity function. So we are looking at this type of equation, and its solution for a probabilist is, of course, a very interesting, very important functional, is the mean exit time or the mean survival time. So its location, again, of the location of its maximum is the safest point, because if you start the process from there, then it takes the longest to hit the boundary where the process gets killed on average. So of course, therefore, you are interested about maximizing this right-hand side by choosing X that way. This is what I call XT. So the torsion for a probabilist is this mean exit time. And what we get from our calculation is this very unassuming inequality or estimate, is again making a difference between the location of well, X star and XT. And we can see it via, well, via V, not directly. We have been trying, to invert this somehow, but this CD doesn't help too much. So somehow we can see that they are in some sense near to one another, but they fail to coincide. Of course, this is pretty weak. I mean, I would like to understand this much better, and especially I would like to understand the mystique behind it. Why these 2 points are so near to each other and still fail to intersect, fail to coincide. So somehow the safest point and the point of highest clustering, this most preferred point, they are somehow intimately related, but at least I don't know why. I think this is where I wanted to finish and say a big thank you.
So thank you very much, Jozsef. It was really, really interesting and inspiring. Any questions? Yeah, I remind you, you can unmute yourself and ask questions by voice.
No, I'm perfectly all right. I'm perfectly all right. So don't worry too much. I know that this is a big story, and
yeah, yes, it's a little
too many
bit.
notes.
Sorry.
Too many notes on the score, you know.
For me, it's very sort of a more physical sort of interpretation, so more sort of to the physics.
Well, I wouldn't deny my interest in physics.
Yes, we could see that. We could definitely see that. Well, okay. Well, thank you very much.
I have one more slide.
Yes, and you have the book as well. Yes.
Yeah, I have a book just in case anybody wants it.
Yes. Okay, so probably you can just guide us through the references.
Oh, dear me. Well,
Yeah.
this is a bit of a too much of a self-advertisement then. It's
Probably
just
the best ones.
it's just too
Yeah,
much.
your
So
favorite.
first of all, of course, I would like to mention my colleague in Pune, with whom I had this work, call it universal constraints on the location of extrema. So the X star story is actually closest taken is being related to this paper. But then there is one direction that you can go as a more purely inclined mathematician. We were able to construct and prove all sorts of maximum principles in all sorts of contexts, and of course for an analyst this is a very basic tool, and we did that for a number of non-local equations, again in domains, but not just in domains. So then related things like this Alexandra Backelman-Pucci, of course you will know, and I have one paper. I'm very proud of it. I'm having one paper on Caputo derivatives, but only one. So this is time fractional, and Virginia Kiriakova was kind enough to take my paper. And then there are all sorts of related issues like the famous problem of Ambrosetti and Prodi, which is a bifurcation problem, that you can have different qualitative, well, you have different numbers of solutions, and the qualitative behavior, which is very much decided by a tunable parameter. And then there's a latest paper on Hopf-Slemmer, which again, of course, is a basic tool in PDE theory. So all this and this line very much has grown out from the X-star story. But like you said, I am deep down somewhere a mathematical physicist. I don't know. I mean, don't tell my employer. But but then, of course, all these other papers which I did with Camille Caleta in Wrocław, we have been looking at all these non-local Schrödinger operators. Well, if I'm now self-advertising so much, then let me just say this much, that I really truly believe in non-local Schrödinger operators. Of course, for a true physicist, there are only two Schrödinger operators. One which is minus delta plus V, and the other one is minus, the relativistic version of it. But really, there are many other operators that are interesting for all sorts of other physics, like anomalous kinetics, anomalous transport, that type of business, but also in nuclear physics. So minus delta alpha half, also for other alphas than 1, is interesting, also for physicists. And I am interested really in the whole bunch of non-local Schrödinger operators, because you really can see even the classical Schrödinger operator and Schrödinger equation in a completely different light. I mean, I was able to understand and try to make other people understand all sorts of phenomena that in the 1980s, 70s, 80s, 60s, people have proven about Schrödinger operators, but in an analytic way, so that nobody understands what's going on. You see a beautiful formula, very analytic, extremely appealing, but why? And if you use probability like I like it very much, then you really see mechanisms. Mm-hmm. Then you really see what is behind that formula. And if you do this in this context of non-local, then the poor old Schrödinger operator, the usual classical Schrödinger operator, becomes just one member of the family. And then you will see, why certain things happen about usual Schrödinger operators as they are known to happen. if you see the whole context, what happens for others. And then usual Schrödinger operators are some sort of a limiting case of non-local Schrödinger operators. And then as a probabilist, you will also realize how untypical Brownian motion is in the whole family of Levy processes and Feller processes. Levy processes are far, far more natural and more widespread than Brownian motion. And of course, it is just our culture that we are teaching Brownian motion and that we have grown up on Brownian motion. But somehow Brownian motion is the uniquely singular Levy process, which is the only odd one out in the whole bunch of Levy processes. And again, you understand all these things if you make this exercise of looking wider than just Brownian motion and usual operators, usual Laplacian. Okay, and then the other story is what? Yeah, this is with Japanese colleagues. This is more mathematical physics motivated. So, for example, you would know about embedded eigenvalues, which we have been proving now for relativistic Schrödinger operators. This was not known for. It was an open problem for, I think, 82 years, something like that. We have proven that they do exist for this type of potentials, and then all sorts of other things. And then if you were having any interest in this multifractal properties, then this is this paper, and I even had another paper in this direction, because these are Gibbs measures. Somebody, the gentleman who was asking me a question, he was saying that he was interested in statistical mechanics. Of course, everything there is, well, not everything, but many things in equilibrium statistical mechanics are revolving around Gibbs measures, because they are describing equilibrium states. And you can take somehow that view when you are describing diffusions again in a potential landscape, and they are going to get you to these Gibbs measures, which are living on Brownian paths. So we have done this. This was somehow way back. And all this is summarized and hopefully is made a bit more intelligible in this book, or these two books now, because they have doubled their length. Okay, thank you once again so very much.
Yeah, thank you so very much, and thank you. Thank you. So I think we finish with the talks for today, and in 45 minutes, some of you who would like to join the exercise sessions, well, either can stay here or join in 45 minutes. Yeah, thank you very much, Jozsef, again.
Thank you, Jelena.
I hope to meet you in person sometime.
Hopefully.
Yes. Thank you.
Take care.
Bye-bye.
Bye.